is now, let me change the topic. So I will discuss about thermodynamics, some heat transfer to thermodynamics. Thermodynamics, as you know, is essentially we need heat. Either you need heat or you got to remove heat. So heat transfer we try to do both. There heating is required, we provide it, where cooling is required, we also provide that one. So in order to do that one, thermodynamics will tell you how much heat you want to do. How much of heat you have got to. That's actually the basic science and engineering. Now, all of you have studied your high school physics. You have heard about gases, liquids, vapors, and solids, and so on. There are three phases of any material, which is actually solid, liquid, and vapor. So now today we will deal with one of the properties of gases, which is actually vapor phase. You would have heard about the names. What about the perfect gas? Have you heard about perfect gas? Perfect gas? That's good. Perfect gas? It's good. It comes in the part of the heat. You start with part of physics and also you start with chemistry also. So what is called a perfect gas, what is called an ideal gas, what is called a real gas. Okay. So let's find out what the difference. Most of the students have to mistake between the perfect gas and the ideal gas. They are not really mistake. We'll see in a moment what the difference is. Ideal gas or a perfect gas, we assume that molecules are point masses, number one. And there are no attractive forces between two molecules. This molecule doesn't know about this one, this molecule doesn't know about the third one, and so on. There is no interaction between molecules. What we say is there are no attractive or repulsive forces between molecules. These are the two assumptions we make. That is, molecules are point masses, there is only a point. And the second thing is, of course, when you define how can it have mass, but it has got this assumption we make. There are point masses, and also there are no attractive repulsive forces between molecules. That's what we say. So assumption we make. So based on that one, we derive this equation 3p by t is equal to constant. So what is the value of the constant? This constant is called what is called the universal gas. Because substitutability gas, it's called the universal gas constant. So what are here actually as a vector, you have to know what the units are. Let me write down what the units are. In R, when you put a U, it means the universal gas constant. And like any of the other numbers, like Avogadro's number, Newton's gravitational constant, Stephen Boltzmann constant, the fixed value of iteration is agreed upon. So what at your stage, I will just round it down to 8314 joules per mole. That is the unit. Number is 8314 and unit is joules per mole. That one looks quite straightforward, but many of the students make mistakes in using that number inappropriately. We'll see what mistakes are likely to make and how to find. So then there is one more gas constant, we call it as just RU, only R without the subscript U. This is the value of universal gas constant divided by the molecular weight. I hope all of you know what the molecular weight is. What is the molecular weight of oxygen? Nitrogen? Carbon? Carbon dioxide? Don't worry, at least you know about oxygen, nitrogen. Okay, let's just say M is the molecular weight of the gas. So what we know is the next one we know is what is called Avogadro's number. Avogadro's number is the number of molecules that are present in 1 mole of a gas. And very interesting thing is 1 mole of any gas, whether oxygen, nitrogen, nitric, carbon dioxide, steam, any gas, 1 mole of it, 1 mole will have how many grams? If it is nitrogen, it will have 28 grams of nitrogen. If it is carbon dioxide, it will have 44 grams of carbon dioxide. If it is oxygen, it will have 32 grams of carbon dioxide. So carbon is a solid, so it will not be there. So unless it goes to the vapor state. Steam. If you take steam, molecular weight of water is 18. So 1 mole of steam will have 18 grams of steam present. Irrespective of the species of the gas, the number of molecules you sit down and calculate will be 6.02 to 1023 molecules. Unfortunately, what so happens is that the entire population, right from the day God created human being, right up to today, if you keep on counting the molecules, you won't have completed it. So they take 6.02 to 1023 molecules per mole. That is, if you take this room, let me say this is about, about 15 meters, 15 meters by about 10 meters, 150 times about 4 meters, 600 meter cubed of the number of molecules of air it has got. No way all the human beings can even calculate that one. Okay? 1 mole is 28 grams of this one, it's as 6.02. You can imagine this much of volume, how many molecules it will have. So that's why I keep on telling you, Professor Kalyan Kumar, if I get the reason I walk around the campus is that way, you will also do that one. Most probably, the air that I breathed when I was a student here, that molecule is still there. So it knows me. So that's the reason I am here. To see that molecule. I don't know where that molecule is, but still the molecule is there. Okay. This is called what is called Avogadro's number. But normally in chemical engineering, people use the kilomole as the unit. Because kilogram is a mass, kilomole is a standard unit. If it is a kilomole, it will have 1,000 times more number of molecules. So per kilo of 28 grams, it will have 23. If it is a per kilomole, 1 kilomole of nitrogen, then we have 28 kilograms of mass and also 6.02 to 10⁻26. Again, 3 orders of magnitude taller. So that is what is the Avogadro's number. Okay, now I am coming to Avogadro's number. This Avogadro's number and universal gas constant, they are first cousins. So what is the relation? We will just see in a moment. So various forms of rigidity, if it is this one, PV is equal to RT. This is for unit mass. If it is for unit mass, if it is 1 kilogram, you take that's why I put V as a lower case. Because this P, as I mentioned earlier, this P, nothing but P by M. Lower case P, you have to mention about the convention in the last class. So if PV is equal to mass is taken off, that is it becomes. If it is, if you take P 1 over, then it becomes rho 1 over specific volume is something like density. So we have P is equal to rho RT or if you got the total volume, N is the number of moles in RU. If you are using moles, number of moles, it can come to a universal gas constant. If it is mass, it will be the characteristic gas constant. So we can also write that in terms of mass, it is V times V equal to M times R times P. M is the mass, R times characteristic gas constant. That's what you got. M is in kilograms, V is in meter cube. Please remember that P pressure you got to use, the units you have got to use is actually pascals. So what is the conversion of Pascal? 1 Pascal, 10 to the power of 5 pascals is equal to 1 bar. 1 bar is approximately 1 they use actually in olden days we used to use what is called 1 atmosphere. The standard atmosphere is 1.0131. That is actually conversion. That is standard atmosphere. Okay, that in older when we studied pressure in terms of atmosphere, now it is no longer used because atmospheric pressure keeps on changing from place to place. Ananthapuramu will be one pressure. If you go to Bangalore, it will be something. If you go to Nilgiris, if you go to Uttarakhand, it will be a different pressure. So there is no point with this. In order to standardize the unit of pressure, we take bar as the pressure. So local atmospheric pressure, we can get it from weather stations, and actually there is an app which actually you can download from local atmospheric area. Okay. So when you are using that one, this is your number of moles. If it is mass, That is the equation so, also, what is the value of universal gas constant? Universal gas constant nothing but Avogadro's number times the Boltzmann constant. You remember the Boltzmann constant came also in heat transfer. Where did it come? In Planck's equation. There was a Boltzmann constant was there. The Boltzmann keeps on coming everywhere. Okay, it's like chemical engineers. There are everywhere all over the place. And mechanical engineers also. So this is nothing but universal gas constant is nothing but a product of Avogadro's number and the Boltzmann constant. Both of them are constants. So, what is the reduction for a perfect gas constant PV process? If you say PV is equal to constant for the perfect gas, everything also is a constant because gas constant is a constant number. The PV product of P is a constant, the temperature will remain a constant. So, constant PV process is also a constant temperature process. So, now let's calculate what is the density of nitrogen standard atmospheric condition. The standard atmospheric condition 1.013 10 to the power 5. Standard atmospheric all over the world that's 15 degrees Celsius, which is actually 288.15 Kelvin. Because we had 273.15 to 15, you get 288.15. Because you might have done one more what's called normal temperature, NTP, and you know done it in chemistry. NTP, understanding that is normal temperature, they get as 273.15. Standard is 15. Nitrogen, the characteristic constant R will be 8314 divided by 28 or divided by U. 8314 divided by 28. That will give you the characteristic. That is what is called the characteristic. Okay, I have learned what is called. This is called characteristic gas constant. One is universal gas constant, characteristic gas constant. Obviously, you must expect that characteristic gas constant will be different from each gas. So, for nitrogen, it will be 8314 by 28 units. What will it be? What will be the units of characteristic gas? I have given you the units of this one. So, what will be the units of this? So the molecular weight, if you put it into kg per kilomole, right? It will be per kilomole, the 8 kilojoules per mole. You take this one is also, I can write it as 8314 times 10 to the power of 3 joules per kilomole. Kelvin. I can make this actually. I'm sorry about that. There is 0.34. Otherwise, it is I'm sorry about that mistake. If I get mistakes, you can also. It is 8314 joules per kilomole or 8.314 kilojoules per kilomole. Yeah, 8.314 joules per mole, which is per joules will be 314. So this will be kg per kilomole. So please make this correction. I'm sorry about that. 8.314 joules per mole. The 8314 is because we am used to that using kilomoles as well. It has the 8.314. I like to keep this one as joules instead of kilojoules because always I basic unit of energy is joule. Power is watt. Pressure is newtons per meter square and Pascal. So I would like to keep the basic units like this. So the thing is to remember the constants in terms of basic units instead of kilojoules and kilowatts. Okay, it is 8.314 kilojoules per kilomole. If it is 8.314 joules per mole, it is 8.314 kilojoules per kilomole. Okay, what will be the universal gas for the nitrogen? R for nitrogen will be equal to, if you want to, 8 joules per kilomole, it will be 8314 divided by 28, because 28 this unit is kg per kilomole, so that will be joules per kg. You can find out how much that number is. If for oxygen, it will be 8314 divided by 32. For argon, it will be 8314 40 for carbon dioxide, 8314 44 and so on. Okay. So if you take standard 8314 by 28 joules per kilogram, that's what happens. Yeah. So the density of nitrogen is V by RT, and we say this equation V by RT. Are you able to see? So if you do the 1.01, is again remember standard atmosphere is 1.01 10 to the 5 Pascal. We said 1.013 bar, 1 bar is 10 to the 5 pascals. So it will be 1.013 times 10 to the 5 divided by temperature is 280.5, R is 8314 by 28. Calculate slash is not. Just check whether that number is correct. Okay, so calculate and check whether that number is correct. Okay? Is it correct? 1.184? Correct, sir? Okay? I think all of you have done the experiment in lab, right? You calculated for anyone, has everyone done the Groshoff experiment? Who are the people who have done the Groshoff experiment? Did you calculate the density of air? You calculated. How did you do that one? From the bottom. So you would have used this equation there. Atmospheric pressure. So for air, the only right now you can see why for air, the molecular unit is 29 instead of 28. Okay? So from there, you see, you do the, let's say that the lab temperature would have been about 27 degrees, so we can take it about 300 Kelvin, calculate what its density is. Okay? Make this atmospheric pressure, keep it same on 0.01 make this one 300, make this one 8314 divided by 29, and tell me how much is the density of gas. That is the number you would have used in your Groshoff number, then you rho squared, that's what you would have used there in your lab. Any experiments, so they require the density of air, Groshoff number, and also the force convection also they require.
Yes, sir.
Yeah, force convection, they also require the density of air.
Calculation of Reynolds number.
Huh?
Calculation of Reynolds number, sir. dV rho by mu.
Okay, again, so people who have done this experiment, you would have done the calculation of rho. This is what you would have done. I want you to double check. And I was saying when I was in the lab, people gave me all kinds of fictitious number for density of air. The moment I see the number, I know this is wrong. See, that is what is trait of engineering. You don't have to get exact number. The moment you see the order of magnitude, power, units, you know whether you are done it right or not. Okay, and the density. 1.177. So it should be about 1.2. The standard density of air is 1.2 kilograms per meter cube. That's what it is. So when you calculate how much of air is in that room, let me give you the dimension of the room. This is roughly about 15 meters. It's 15 meters by 10 meters by 4 meters. What is the volume of the room? 15 times 10 times 4. 10 times 150 times 4. That's 600 meter cube. Okay? The density of air is 1.2 kilograms per meter cube. So how many kilograms of air is there?
आज पीछे ये मालूम volume of room was 600 meter cube.
Room dimension 15 by 10 by 4. Enta namma room 15 by 10 by 4. 15 by 10 is 150, 150 times 4 is 600. So total volume is 600 meter cube. And the density of air is 1.2 kilograms per meter cube. So 600 times 1.2 should give us 720 kilograms of air is there. So 720 kilograms is a huge amount. If you all are traveling, one of you will not be able to carry it. All 69 of you are going to carry, each of you carrying about 10 kilograms of air. Just to give you a physical feeling of that. That was a very low of pressure, 1.013 bar, and also the 2.2 kilograms per meter cube. That was 615 by 15 times 600 meter cube. 720 kilograms of air is in this place. Okay. Right. Now, this is all clear? How do you calculate the density of heat? This is what you develop in the lab. The calculation of Reynolds number, the Grashof number, and other things you calculate. This is basic. Example. What is the volume of weight with 1 mole of nitrogen at normal atmospheric pressure condition? Remember, I am not using the word standard. I told you standard is 215 degrees Celsius. Normal is 273.150 degrees Celsius. So 1 mole of nitrogen, the mass is 1 mole. 1 mole will come by not to get 1 kilomole will come to 8. The pressure is this one. The temperature is this. Gas constant 8314 by 28. So what is the volume? MRT M 0.028 8314 by 28. Calculate this. So this is the volume that is occupied by 1 mole of the gas. Occupied 1 mole of nitrogen at normal conditions. So calculate that. Let us see that number. That meter cube together. I hope you guys and girls know how to convert meter cube into liters. How many liters make 1 meter cube? 1000. Okay, then convert into liters and tell me how much it is. Don't copy from there, you can calculate that. Okay? Don't copy from there.
Simple. Agree, 0.0124183 meter cube into 1000. Just the liters looks like 22.4183. In chemistry or physics, you would have studied in your high school. 1 mole of a gas at normal temperature and pressure will occupy 22.4 liters. You have done that for long time? 22.4. 22.4 is the magic number. Right? What is that? That's what you have studied. Is there a familiar rule that 1 mole of a gas actually, it doesn't matter which gas it is. There's a nitrogen, oxygen, they all occupy the same amount of volume. It's 22.4 liters. NTP is 273.15, just recalculating, and these are the two different NTPs. You have also got to specify at what temperature you are calculating. Now, earlier you have seen from the number of degrees of freedom, you need two properties to specify: pressure and volume, pressure and temperature, or temperature and volume. Any two properties you give for a pure fluid, you get the entire thing specified. That's because you are gas constant will be equal to RT. If you know two of them, gas constant is a constant, is a specific number, you'll be able to calculate the third parameter. Okay? Alright. Now, when can the gas be treated as a perfect gas? What is assumption we made? The assumption we made was all the molecules are point masses and there are no attractive or repulsive forces between the molecules. But compound molecule, real gas is not a point mass because it has got a specific volume. There is specified volume, however small it is. For example, helium will have a small diameter, argon larger, krypton even larger, oxygen also larger, steam will be smaller, and so on. So it has got a specific volume. For most of the gases, we can treat them as perfect gases when there are low densities, very low densities, or pressures very close to atmospheric or below atmospheric pressure.
We will not be making a very big error if you apply that one to slightly above the atmospheric pressure also. But where it stops, we will see it later. A perfect gas is one. How do we distinguish between perfect gas and ideal gas? Both perfect gas and ideal gas follow the gas law of CP is equal to RT. There is no doubt about it. Both of them will follow. But what makes a difference between perfect gas and ideal gas is what you got to understand. Especially as chemical engineers, it's absolutely imperative that you understand that. A perfect gas is the one which has got constant specific heats do not change with the temperature or pressure. So when I say specific heat of constant pressure, specific heat of air is 1 kilojoules per kg Kelvin, it stays at 1 irrespective of temperature and pressure. That is for a perfect gas. The perfect or ideal or real, they are distinguished by how the specific heats behave, not really how the molecules behave. Let's get that one. So a perfect gas is one which has got constant specific. Then what is ideal gas? Ideal gas is the one which obeys the above. If still it obeys the is equal to RT, no doubt about it. But the difference is, but the specific heats are only functions of temperature. The specific heats actually go up with temperature. For all the any gas, a specific heat keeps on going up. As a higher temperature, we have a higher specific heat. What does that mean? And heating air, for example, air heating, you use in most agricultural processing and so on. And to dry and hot air, it grains and dry it. So if you use at room temperature to heat share, specific heat will be some value. Okay. Technically, at higher temperature, this specific heat is more. That means for the amount, but heating the same amount of gas, you need more heat. This is what it means. So as the temperature goes up, the specific heat actually goes up. For all the gases, this is what happens. Okay. And it's a monotonic. There is nothing like going up and coming down. Constantly it keeps on going. As the temperature goes up, specific heat keeps on going up. So for the ideal gas, the specific heat is only a function of temperature. Then what is the real gas? Simple. What are the two properties that we talk about? Two intensive properties, pressure and temperature. Real gases, the specific heats are functions of both temperature and pressure. That's what I think. So if you take let me just remove this and write it down for you, recapitulate. CB and CP, perfect gases, CB and CP, ideal gases. CB is a function of temperature and CP is a function of temperature. If you write as a function of temperature, CB and CP are real gases. CB is a function of pressure and temperature, and CP is also a function of pressure and temperature. That's also the distinction between perfect gas, ideal gas, and real gas. For real gas, I mean V is equal to RT doesn't hold true. Then what are the various equations of state are there? We will see that in a moment. Point here. Alright, let me take a breather and ask this way if I got any questions. I got through too many fundamental things. Has anyone got any questions about this? Nothing? Something you don't understand? Something you want me to repeat? Anything? Nothing? It's all clear? Clear like a crystal? Okay, now let me ask a question. Take water at room temperature. Okay? Temperature 300 Kelvin. Okay? What is the density of water you are using in calculations? What is the density of water? 998. Okay, let me round it to 1000 to make your life simple. Okay? Now the pressure is now 1. That is equal to 80. Mark 1 kilometer. What H2 over H2 8900. Pressure is 1.013 into 10 to the power of 5 pascals. Okay? Apply PT is equal to RT, if we see it is satisfied. Calculate P or P is equal to rho RT. Okay? Check whether it is satisfied. ఫ్లో ఉంది, ఆర్ ఉంది, టెంపరేచర్ ఉంది. మూడు క్యాలిక్యులేట్ చేసి చెక్ వెదర్ యు గెట్ ది ప్రెషర్. You know, earlier I said that P is equal to 1. ఈ equation apply చేద్దాం. Rho is 1000, R for water 83145 by 18 multiplied by 300. How much extra then? So what is wrong? There is a mistake. Come on, guys, answer the question. There is a mistake. Please go to what the validate the water apply gas cover, very good. The gas cover. So after gas is then it will for gas. This is water is the liquid. Okay. Number one. Second thing is water, the molecule of substance becomes liquid only when there are lot attractive forces in it. So attractive forces on dictation. So you cannot apply heat is equal to optimal liquid. Please remember that one. That's not taken care of. It's only for gases. If they are low pressure, high pressure, you cannot apply that one again. So that's why it isn't applied. So this P is equal to RT is the whole calculation is wrong. So I cannot apply ideal gas equation to this. That's possible. Okay, that's it. Okay, when we go to next slide, I hope you understand that one. This is a long. We come to properties of liquid bit later. So now what is the real gas? Ideal gas and real gas, but they are all called equations of state. Equations of state, but P is equal to RT is what is real gas equation of state? A real gas obviously is not would be because it has got a finite size and it has got attractive repulsive forces. One of the oldest forms of real gas equation of state is what is called Van der Waals equation of state. Van der Waals was a physicist who got the first Nobel Prize in physics way back in 1904. He is a Netherlands or Dutch physicist who got that Nobel Prize. So he proposed that for real gases, we know that there are finite size and also there are not attractive repulsive forces. And again, attractive repulsive forces, like you have seen in radiation, attractive repulsive, they are proportional to square of the distance which they are separated. But if you are too far off, you feel like going, everyone feels like going to US and taking money because it's so far off. There are a lot of dollars, life is so easy, they got cars and they got like bungalows and everything. But once you go start living there, you see what the problems are. But Nalla not get the weight test తర్వాత మాట్లాడే భాష వాళ్ళకి అర్థం కాదు, మన తిండి అర్థం కాదు, మన ఆడే ఆటలు వాటి అర్థం కాదు. సో దెన్ యూ హ్యావ్ దెర్ ఇస్ వెన్ యూ కమ్ టూ క్లోజర్ దే become very repulsive. Is sorry to mention about this. When you are newly married, there is so much of attraction to husband or wife. But the time goes on, they keep on fighting. So that's when you become familiarity meets contempt and when you are too far off, there is attraction. When you come too close, you are saying positive, negative part of it. So what Van der Waals found out is that you have to account for the attractive repulsive forces, and you also account for the size of the molecule. So what he did was, in volume rho, he controlled a parameter called B and then decision. B minus B, that B takes care of size of the molecule. So to give you physically how exactly we interpret that one is like this. Originally we thought that molecules are only 5 masses. So except now the distance was only this much. Okay? Now when the molecule has got a finite size, so now although we say center to center distance equal to how many, but the distance is different from the distance dimension. So what he did was he corrected that one by taking the diameter of the molecule, and that B is actually proportional to the diameter of the molecule. It's something to do with the don't worry about the distance decision. So that the distance between molecules is taken care of. So it's no, and he is attractive repulsive force. He takes care of by factor A divided by B square. Then B is actually, that is actually capital B. I put as a capital B. Of course, especially M here, because this I am writing for 1 kilogram M or T. Because it's 1 T is equal to M is equal to 1. I can still write that one. The constant A takes care of the attractive forces, because in gases there are what is called attractive repulsive forces are quite small. Only attractive forces are dominating. In liquids, repulsive forces are also present. When the molecules get too close, then there will be repulsive forces. When they are too far, like it out, if they are too far, it always attractive. I think that going to Australia or New Zealand, because I live in Australia, I know what the negative things are there in Australia. So that's why half the time I am spending in India. So that's what the A takes care of that attractive forces, B takes care of finite volume of the molecule. So this is what is called the basic, what is called Van der Waals equation of state. It's also termed as, at this stage, let's write out, this is called a cubic equation of state. Why is this cubic? Most of the equations of state that are used all over by chemical engineers, they are all cubic equations of state. There are numerous equations of state now available. Van der Waals, Redlich-Kwong, Swale. What are the equations? Everyone, the moment you know how to take care of it, each one gives a little bit of it, and he gives a name of his own. There are so many equations of state. And which one should I follow? As a young chemical engineer, you want to go to field, and your boss asks you to calculate PVD properties of gas. Which one you use? All over the world today, the standard is there is what is called Helmholtz free energy based equations of state. They are all over the world. They are state. It is neither Van der Waals equation of state, nor perfect gas equation of state, nor ideal gas equation of state, nor Redlich-Kwong. They are called Helmholtz free energy equation of state. I am just giving you this information, but don't worry what is Helmholtz free energy, what is the equation of state. It's a very complicated thing. But only thing is, I want you to remember when someone says Helmholtz free energy, you must say, yes, I heard that one in my thermodynamics class. I want you to remember Helmholtz free energy. So later on, we will see that what is called Gibbs free energy. That will come in from third year thermodynamics, Gibbs free energy. So that is the world standard equation of state. Because most of the equations of state for all the properties that we have, they are all based on Helmholtz free energy equation of state. However, for real gas equation, actually the PV is not equal to R. Because obviously the PV particularly is equal to R. What people do is that we are all busy. Can I make some data correction factor and then make sure that this is valid? So what we do is that the quantity that this inequality is removed by making PV by RT is equal to Z. Some constant, but that Z will be again a function of pressure and temperature. That Z is what is called a compressibility factor. Then what is called compressibility factor. For an ideal gas, obviously, and the perfect gas, we will see that Z will be always equal to 1. For real gas, it won't be equal to 1. It will be greater than 1, it will be less than 1. But we will see with later how the compressibility of the gas varies with pressure and temperature. We will see, because real gas depends upon pressure and temperature, properties related to pressure and temperature. So how the compressibility factor varies, which will be also a function of pressure and temperature, we will see with later. At this stage, I wanted to introduce the terminology, compressibility, Van der Waals equation of state, Helmholtz free energy, all these. All the names I am going to drop in now. treat them like black boxes. We'll just open each box as we go along. Okay, real gas specific heats are functions of temperature and pressure. That's what we written there is only function of temperature. Okay. If you breather. Is it clear? Any questions? You know what is ideal gas is? What is real gas is? What is perfect gas is? And you know what Helmholtz free energy, what is the equation of state? Van der Waals equation, and so many other equations of state are there. And finite volume of the molecule has got to be taken care of, and attractive forces are there. Repulsive forces are not taken care of here in Van der Waals equation, because in gases, seldom there are repulsive forces there. Okay? And proceed further. Next slide. Now, we said that they are all functions of specific heats. Now we have to say what is specific heat. In physics, what is the definition of specific heat? What is the definition of specific heat? One degree Celsius. Okay. Amount of heat energy, is everyone agreement with you? The amount of heat energy required to raise the temperature by 1 degree, it is specific. If it is water, it will be some value. If it is iron, if it is wood, it will be some other value. Okay? If it is xylene, 1 kilogram, it will be different value. So specific heat. So specific heat you are raising the temperature. So the specific heat for gas, there are two types of specific. One is a constant volume, another what is the constant pressure. We will come to that in a moment. The basic thermodynamic definition of specific heat is this CE. And remember, again there is what is called international notations are there. We have got to follow them. This international notation is exactly like your road rules. If you just road left side right side also coming in opposite direction. You can no right turn attack right turn just you can no parking attack parking just. But usually to make life simple, there are some road rules we have to follow. If there is no parking, you should not park there. What I told you, if you are in a class, if you are coming by 11:30, you should come and you should not talk, you should not. If you take the calculator, you have to take there are some rules you have to follow. Next, quite simple, that's all, that's why we are doing. Not that you have to trouble. If everyone follows the rules, I can guarantee not a single road test will be. Speed limit on highways is 80 kilometers. You have to drive over there, you have to 3 గంటలు 8 గంటలు. But check the button. 3 గంటలు హైదరాబాద్ వెళ్ళాలంటే it should hang in his neck. So he is being not only that is endangering his life, he is endangering other people's lives. Some people have seen so many times, fellows driving too fast, a median cut chase, ఎదురుకుంటూ వచ్చే బండిని పడతారు. How many accidents have occurred between Kallur and Kutte? Every day, the newspaper first thing is about accident. ఎందుకైంది వాడు 20 కిలోమీటర్ల దూరం 90 చచ్చిపోతారు వాడు చేస్తారు ఇంకొక చెప్తారు. So these are some rules we have to follow. So similarly, the international notations కూడా మనం రూల్స్ అన్ని ఫాలో అవ్వాలి. ఎందుకంటే ఇప్పుడు ఇవాళ మీరు ఇండియాలో పనిచేస్తున్నారు, ఇప్పుడు టుమారో యూ విల్ బి వర్కింగ్ ఇన్ నెదర్లాండ్స్ ఆర్ ఫిన్లాండ్ ఆర్ యూ విల్ బి వర్కింగ్ ఇన్ జపాన్. So if you use your own convention, that fellow will not understand that. So there are some conventions out there, and there is a standard next handbook called what are the international conventions for each units and what are the values. You can actually download from the internet of free detail. So we have got a specific heat definition for this. Specific heat we use in lower which is not capital C. Let's say lower case C. Whenever you put a substrate that is what they give a constant. Specific heat and constant volume is defined as a partial derivative of internal energy. U is internal energy because it's a partial derivative and the temperature at constant volume. Because it's a constant volume, du by dt at t is equal to this volume. That is a definition of the specific heat in thermodynamic definition. Okay? If you really see technically, it is actually an example of it is the amount of energy required to raise the internal energy of 1 kg of any specified specimen to 1 degree Celsius. It is internal energy. Okay, that's what we have. Whereas their heat energy, there are two ways. In thermodynamics, we differentiate between the heat, that heat and the other Q heat and U heat. There are two heats again. The internal energy source. There are two. One is what is called the internal energy U, another is what is called the enthalpy. So specific heat constant volume is based on internal energy U by dt. So obviously, when we put this one, we put a partial derivative. But partial differentiation. We don't partial differentiation. Have you done partial derivative?
పార్షియల్ డెరివేటివ్స్ చెప్పారు కదా మ్యాథ్స్.
Partial differentiation.
డో సింబల్ చెప్పారు కదా.
Not D, delta or D.
డో
You have done that one in maths?
డో యూ బై
Partial
చెప్పారు కదా.
derivative. Okay, this is the, you must be familiar with it. This is partial derivative.
చదివినారు కదా చెప్పు.
Why do we say partial derivative? That is a technical definition. But for an ideal gas, because it's only a function of temperature, so I can replace this one by I can make it du by V. Similarly, enthalpy we defined as H equal to U plus Pv. You remember the other day I showed you what is a property called enthalpy, which is nothing but U plus Pv. I don't know whether you people recollect that or not. Let me see this slide and show what. That one is slide. It was in the last class. So I showed you this Pv plus U. I asked you to treat this on the black box. Pv plus U is called H. So T of Pv plus U is H. So that is what is the term. Obviously, enthalpy will always greater than internal energy. Okay? Pressure cannot be negative, and volume cannot be negative. The written negative of the add the passage quantity with this quantity, whatever this quantity has come with this one, we are always greater than negative. So for any substance, not only gas, liquid, solid, or whatever it is, enthalpy will be always greater than internal energy. But remember that for the steam, everything that will be. Going back to this. The specific concept method is defined as partial derivative enthalpy instead of internal energy. Again, for an ideal gas, because again the U is only internal property of internal energy, the only property of temperature. Obviously, for ideal gas, Pv is also a function of only temperature because Pv is equal to RT. So, any sum of this, each of them is a property of temperature. So, enthalpy has also got to be a property of temperature only for an ideal gas. So, the specific concept pressure is defined as a partial derivative of enthalpy times temperature, which is pressure is constant. So, this is something that so, for an ideal gas, you can always replace this partial derivative, not the derivative, dH by dt. That's what it is. Okay, what I will do is, okay, let me get through this part. Now, we know that H is equal to U plus Pv. So, let us differentiate. dH by dt refers to temperature. dH by dt will be du by dt plus dt by dt. Pd by dt. Correct? I differentiate just about P, but Pd is equal to RT for a perfect gas. This is equal to RT. So, T R times, this will become R times T of Pd by dt equal to R. So, this quantity will become equal to R. Correct? Just put your pencil on the paper, then you will see that Pd will be equal to R. Pd is equal to RT. R is a constant. You pull it out of your brackets. So, it will be R Pt by dt is equal to 1. So, it will just become R. So, dH by dt is equal to Cp. And du by dt becomes this. Okay, that is ideal gas. Because here we are substituting Pd is equal to R. This will be Cv. So, specific heat at constant pressure is equal to specific heat at constant volume plus the gas constant. The consistent units, if I am using joules per kg Kelvin, it will be a cross. If it is joules per mole, it will be a, or even if you are using moles, this specifically will be so many joules per mole Kelvin, this will also joules per mole Kelvin, R will also be joules per mole Kelvin. Yes, R joules per mole Kelvin, or per kilojoules per kilomole Kelvin. Or if you want to use it as mass basis, this can be joules per kg Kelvin, this is joules per kg Kelvin, this is also joules. As long as the consistent units. Now again, let us see one more thing. Cp is always greater than Cv. Why? Cv is some number, R is universal gas constant. Gas is gas constant depending upon mole or mass. There is always a positive number. It's not negative. So when you add a positive number to any given number, this number has got to be greater than this number. So another thing that we got to learn is a specific heat at constant pressure will be always greater than specific heat at constant volume. Okay? Specific heat at constant volume, function of temperature for ideal gases, it is partial derivative of internal energy. Specific heat at constant pressure is a partial derivative of enthalpy at constant pressure for ideal gas. For an ideal gas, once again, specific heat at constant pressure will be always greater than specific heat at constant volume. So this is one way of checking. When you make a calculation, so I think you come to conclusion that specific heat at constant pressure more than specific heat, if you know that you have done some mistake somewhere, you got to correct it. So these are all the fundamentals you got to remember. The specific heat of depends upon the R, so you tell out if it is the mass, if you choose per kg Kelvin. Okay? Right. Now I'll stop there today. I will take up some next step. Okay? Now, so now we have understood the difference between ideal and perfect gas. We have defined the specific heats, constant pressure, constant volume. And also what is the difference, what is the relation between the specific heat and constant volume and constant pressure. Okay? Clear? Any questions? No? I see blank faces, blank. I don't know if you understood. No one has got any questions. There should be some questions at least at some point. Anyway, don't worry about all this thing. I don't want to do the notes halfway through the whole chapter is completed and just upload it. I'll give it to Professor Nashikaran and I'll give it later. The same thing about radiation. I'll pass it on to Professor Kalyanama, will pass it on. I'm waiting for the whole chapter to be completed. If they give the whole notes at one play, one go, you will not appreciate it. Otherwise, you won't listen to what happens. Okay? It's good? Okay. And please read this once again when you go back. When you read again, then you will have questions and you ask me questions. Okay, good. Let me take the back.